Hey everyone, and welcome to a deep dive into something really, really fascinating. We're talking about a crisis in cosmology.
Yeah, that's right.
Cosmology, the study of the universe
Yeah.
on those grand, massive scales. The whole universe.
Yeah.
And we've got this awesome article called The Crisis in Cosmology. And wow, it's causing quite a stir, let me tell you.
Yeah.
It's making scientists question some of the basic stuff we thought we knew about the universe. So get ready. It's going to be a wild ride today.
It is pretty wild. It's like, think of it this way. It's kind of like you've been using this map to navigate, and then all of a sudden you realize that map, it might have some serious inaccuracies.
Oh, I see what you mean.
Yeah.
Yeah, that's a great analogy. Okay, so to kick things off, let's talk about what we thought we knew, right? For years now, the big cheese, the reigning champion in cosmology, has been this model called the Lambda CDM model.
Yeah.
Can you kind of break that down for us? What is that all about?
Yeah. So the Lambda CDM model, it's often called the standard model of cosmology. And the reason for that is it's been incredibly successful at explaining a whole bunch of observations that we've made about the universe. You can kind of think of it like a recipe, a cosmic recipe.
Hmm.
And it's got two key ingredients.
Okay. I like where this is going.
Yeah. The first one is dark energy, and that's represented by the Greek letter lambda.
Oh,
And the second ingredient is cold dark matter, or CDM.
CDM. Got it. Okay, so let's dive into these ingredients a little bit. What's the deal with dark energy?
So dark energy is this mysterious force, right? And it seems to be causing the universe's expansion to actually accelerate.
Whoa.
Yeah. It's pretty mind-blowing. Like imagine a balloon, right? And you're inflating it.
Okay. Got a link.
So that's kind of how the universe is expanding. But get this, instead of slowing down, which you might expect, like if you let go of a balloon, it's going to,
Right, it would.
yeah, lose its,
It's speeding up.
whoa.
The expansion is actually getting faster.
And dark energy, we think, is the culprit.
Wow, that's wild.
Yeah.
Okay, so then what about cold dark matter? What is that all about?
Right. So cold dark matter is this, well, we think it's this invisible form of matter. And it doesn't really interact much with light or with regular matter.
Okay.
And that's why it's called dark,
Oh, okay.
because it doesn't emit, absorb, or reflect light.
Gotcha.
So we can't see it directly.
Tricky.
But we believe it's out there. And we think it's responsible for this large-scale structure of the universe. So you can almost think of it like the scaffolding. It's what's holding galaxies and galaxy clusters together.
Oh, interesting. Okay, so we got this, seemingly great recipe, right? It explains things pretty well. But then this article comes along, The Crisis in Cosmology, and it throws a wrench in the gears.
Mm.
It says there are cracks in this foundation. So what's going on? What are these cracks?
Yeah, you're absolutely right. The article highlights these recent findings, and they're really throwing a wrench in the Lambda CDM model. It's kind of like we followed the recipe perfectly, but the cake isn't rising the way we expected.
Interesting.
Something's not quite right.
Okay, so what are the wrenches? What's going wrong?
So one of the major discrepancies that we're seeing has to do with something called the Hubble constant.
Okay.
And this constant, it's basically a measure of how fast the universe is expanding.
Okay, got it.
So here's the problem. We're getting different values for the Hubble constant depending on how we measure it.
Oh, really?
Yeah. So one method that we use is based on observations of something called the cosmic microwave background.
Okay.
And that's basically the afterglow of the Big Bang.
Yeah.
It's like this faint radiation that's left over from the very beginning of the universe.
Okay.
But then another method that we use is based on observations of these really distant supernovae, these exploding stars.
Mhm.
And the problem is the values that we get from these two different methods, they don't match up.
So it's like, I'm trying to think of an analogy here. It's like trying to measure the speed of a car
Right.
using two different speedometers, and they're giving you two different speeds.
Exactly. That's a great analogy.
Okay.
And the thing is, it's not just like a little rounding error. It's a significant difference.
Mm.
And what this suggests is that maybe our understanding of the very early universe, it might be flawed. Or maybe there's something really fundamental that's missing from our current models of how the universe evolves.
Okay, so that's already one pretty big wrench.
Right.
Are there any other sort of discrepancies that are making scientists scratch their heads?
Yeah, there's another one that's causing a lot of buzz. It's called sigma 8.
Stick away.
And this one, it's a measure of how clumpy matter is in the universe.
Okay.
So basically, it tells us how much matter is clustered together in certain regions of space. And again, what we're finding is that the measurements of sigma 8, they don't quite line up with what the Lambda CDM model predicts.
Hmm.
So the observations are suggesting that matter actually seems to be clumping together more slowly than we would expect based on our models.
Oh, interesting. Okay, so we've got this Hubble constant problem,
Mhm.
and we've got this issue with sigma 8.
Right.
And they're both painting this really puzzling picture.
Yeah.
And I think this is where this new study comes in, right? The one using gravitational lensing.
Exactly. You're on the right track.
Okay.
So this new study, it's pretty exciting. It's using data from the Dark Energy Survey, which is a really cool project. And it's helping to shed some new light, literally, on these discrepancies.
Okay.
So you know gravitational lensing, right?
Yeah, I've heard of it.
Okay, cool. So just as a quick recap, gravitational lensing happens when the gravity of some really massive object, like a galaxy cluster,
Hmm.
it bends the path of light that's coming from a more distant object that's behind it.
So like a cosmic magnifying glass almost.
Yeah, precisely. Yeah, you got it.
I
It's like if you imagine, putting a bowling ball on a trampoline.
Okay.
The bowling ball is going to create a dip in the trampoline.
Right.
And then if you roll a marble nearby, the path of that marble is going to bend because of that dip, right?
Yeah.
So it's the same kind of thing happening with light and massive objects out in space.
Oh, that's a good way to think about it. Okay.
Yeah, so what this new study found is that the universe, it actually appears to be clumping together even more slowly than what the Lambda CDM model would suggest.
Oh, wow.
And the key here is that these results, they're statistically significant. So that means it's really unlikely that they're just due to some random chance or some fluke in the data.
Okay. So we've got these discrepancies. They're not going away. They're statistically significant. And it's causing a real stir in the cosmology world.
Definitely.
But what could be causing them? Like, I guess the big question is, do we need to just toss out this whole Lambda CDM model and start from scratch?
Hmm.
Or is there something else going on?
That's the million-dollar question, right? It's what everyone's trying to figure out.
Yeah.
And there are two main possibilities that are being explored right now.
Okay.
So the first one is that maybe we just need to tweak the model a little bit. Like maybe we need to modify the Lambda CDM model.
So, like, adjust the recipe, not throw it out completely.
Exactly. Maybe we need to add a new ingredient or change the proportions of the existing ones. So, for example, maybe dark energy is not actually constant, as we've been assuming. Maybe it changes over time.
Okay.
Or maybe there are other factors, other ingredients that we haven't even considered yet that could account for these discrepancies.
Interesting. So we're not giving up on Lambda CDM just yet?
Not necessarily, no. There's still hope for the standard model.
Okay.
But then there's the second possibility, and this one's a little more radical.
Okay, I'm intrigued.
Yeah. The second possibility is that we might need to come up with some alternative theories of gravity.
Whoa. Okay.
Yeah. So what this means is that our current understanding of gravity, which is based on Einstein's theory of general relativity,
Right.
it might actually be incomplete.
Wow.
Yeah. So maybe there are aspects of gravity that we just haven't fully grasped yet.
That's a big one. Like Einstein's theory, it's been so successful at explaining so much,
It has, absolutely.
Like, are there any specific alternative theories that are being, like, kicked around out there right now?
Yeah, there are actually a number of different contenders out there,
Hmm.
and each of them has its own strengths and weaknesses.
Okay.
So some of these theories, they propose modifications to Einstein's equations,
Okay.
and then others, they introduce entirely new concepts. So it's a really active area of research right now. There's a lot of excitement and a lot of debate going on in the physics community.
Okay. So this is all fascinating, and I'm sure it's really important for the scientists who are working on this stuff.
Yeah.
But I think a lot of people might be wondering, like, what does this all mean for me? I'm not a cosmologist. Why should I care about this so-called crisis in cosmology?
That's a great question. And, it's about more than just like tweaking some equations or coming up with new theories. It's really about pushing the boundaries of our understanding of the universe itself.
Hmm.
It forces us to question the things that we thought we knew. And it opens up all these new possibilities for exploration and discovery. And I think on a deeper level, it's also about that sense of wonder and curiosity that we all have.
Right.
The desire to understand our place in the cosmos. It's
Yeah.
a fundamental part of being human.
And, it really makes you wonder what other surprises the universe might have in store for us.
Yeah.
Right? Like, if we're wrong about some of these fundamental aspects of cosmology, who knows what else we might discover?
Exactly. That's the exciting part. It's like we're just scratching the surface. And this is how science progresses, We make these new discoveries, they challenge our existing knowledge,
Mhm.
and that leads to more questions, more research, and hopefully a deeper understanding of the universe.
Wow. Well, this has been a fascinating deep dive. Thanks for taking us on this journey.
It's been my pleasure.
And to all of you listening out there, thanks for joining us.
Yeah.
And until next time, keep looking up, keep wondering, and who knows what amazing discoveries await us in the vast expanse of the cosmos.
Absolutely.